Okay, so here's a little warm up for you. A fair coin is equally likely to land heads up or tails up. The key idea, one of the key ideas here is equally likely, because if the outcomes are not equally likely, we can't deal with this probability the way we do. But it's equally likely to land heads up or tails up. Suppose you toss a fair coin 3 times. What is the probability that the coin will land tails up exactly twice? Explain your reasoning. So here you go. And by the way, you can pause it here and you can write your answers out before you watch me, because it feels so much cooler when you say, yep, see, I did it. Okay, so pause the video now and take a try at it. Okay, so what's the first flip do? What's going to happen on the first flip? Well, we can say you're going to either get heads or tails, right? And then from there, what happens? Well, we kind of have this idea that we have these two different realities, one where we got heads, one where we got tails. So we're going to explore them separately, okay? And what we're going to say is, okay, if you got heads, what happens there? Well, from there, you could have gotten on the second flip either heads or tails. And if you got tails first, you also could have gotten heads or tails on that second flip, okay? And now we've got 4 kind of different realities where we got heads and heads, heads and tails, tails and heads, tails and tails. Okay? And now we've got to flip it a third time. And what do we get? Well, we could have got heads or tails for each one of those outcomes, right? And so then how many different possible outcomes did we get? We got these 8 outcomes where you either got heads, 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 and that you can just follow the path through, or heads, heads, tails, heads, tails, heads, heads, tails, tails. These are all the different possible ways that you could have gotten your 3 flips. Okay? And they're asking for the probability the coin will land tails up exactly twice. So which ones have tails up exactly twice? We need 2 T's. This one, and this one have exactly tails twice. Okay? So how do we talk about that as a probability? We say out of the total of 8 outcomes, 3 of them had the preferred outcome. And so the probability that we'll get tails exactly twice is 3 out of 8. And if you wanted to turn that into a percentage, you can do 3 divided by 8. Then you'll get a decimal of 0.375. And that could be an answer. You could express it that way as a decimal, 0.375. Or you could turn that into a percent as 37.5, moving the decimal over twice. So we're going to be this is just kind of a warm up of what does it look like to have probabilities, and the probabilities that important parts are that the outcomes need to be equally likely, and that we express it as favorable outcomes over total outcomes. And you can do it as a fraction, decimal, or percent. But we're going to be doing it with lines and with areas. And let's take a look at that. Okay, so in the solve it, you found the probability involving a coin. In this lesson, you will find probabilities based on lengths and areas. The probability of an event written as the probability of this happening, P parentheses, and then whatever that event is. Sometimes that there's kind of notation that keeps it from writing it out in words, but the probability of this particular event, or P parentheses, whatever, is the likelihood that the event will occur. When the possible outcomes are equally likely, the theoretical probability of an event is the ratio of the number of favorable outcomes on the top to the number of possible outcomes on the bottom. Recall that a probability can be expressed as a fraction, decimal, or percent. So the essential understanding here is that you can use geometric models to solve certain types of probability problems. And since we're in geometry, that's what we're going to be doing. Okay. In geometric probability, points on a segment or in a region of a plane, meaning some geometric figure, two-dimensional figure, represent outcomes. The geometric probability of an event is a ratio that involves the geometric measures, such as length or area. We're going to express them as a ratio of lengths or areas. Okay, and the key concept, it's not a theorem, but it's one of these theorem type things, is for probability and length, particular length, you say, okay, if point S is the thing that the outcome, okay? Point S is on AD, this is from A to D, the segment is chosen at random. You just pick some point. The probability that S is on BC, this part of that segment, is the ratio of the length of BC to the length of AD. So if this is 2 units long out of the total, AD is 6, then we would say BC over AD, or 2 out of 6, which is 1/3, right? The probability of S landing on segment BC. Okay, that's the idea. We're going to do a problem or two with that. Okay, so using segments to find probability, point K on ST is here from 2 to 14, is chosen at random. What's the probability that K lies on QR? Okay, well, we need to find the lengths of those particular segments. And how can you find the length of each segment? You can use the ruler postulate. And what the ruler postulate says is that if you take the two values that they land on, 2 and 14 in this case, and you subtract them, 2 minus 14 is negative 12, and you take the absolute value, then you get 12, okay? Or you can always start with the higher minus the lower, that also works, but you can just go from anywhere. You can say 2 minus 14, and then take the absolute value, and that is 12, okay? So that's 12, and what if we did that same ruler postulate for QR? Well, we take 5 minus 8 is negative 3, absolute value of that is 3. So then we get 3 over 12. And if you simplify 3 over 12, you get 1/4. Yeah, so, oops, length of QR, 5 minus 8, absolute value of it is 3. Length of ST, the whole thing, 2 minus 14, absolute value of that is 12, and that simplifies to 1/4. So we can say that the probability that K is on QR, when K is the random point that we picked between S and T, if it's on QR, there's a 25% chance of that. Now, your got it problem. Use the diagram in problem 1, and point H on ST is selected at random. What is the probability that H lies in SR? So pause your video now, calculate that, and when you think you have your answer, come back. Okay, so we already know what ST is. We calculated that earlier, and we said ST is 12 units long. So what we need to find out now is, what is SR? And SR is from 2 to 8. Well, what is 2 minus 8? 2 minus 8 is negative 6. The absolute value of negative 6 is 6. So that means that there are 6 units of length for SR, and that means 6 out of the 12 units are the preferred outcome, and that simplifies down to 1/2, or 0.5, or 50%. Yep, there's your answer. Okay, let's keep going. Okay, this one's kind of cool because it actually involves a type of line called a timeline. Okay, timeline. So, using segments to find probability. Problem 2, transportation. So there's a commuter train that runs every 25 minutes. If a commuter, a person who's going back and forth to work, right? If a commuter arrives at the station at a random time, what's the probability that the commuter will have to wait at least 10 minutes for the train? Okay, so here's this number line that represents those 25 minutes. Here, 5, 5, 10, blah, 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 okay? Now, here at the end, at 25 minutes, this is the amount of time since the last train left, right? So this is 0 since the last train left. And if you arrived after the last train left, then you have, if the person arrives within here 15 to 25 minutes, they are going to wait less than 10 minutes, or 10 minutes or less, right? So it says for at least 10 minutes, that means all the times where you didn't get there within 10 minutes of the train arriving. So you have to wait at least 10 minutes. And that's this whole section right here, represented as this. Okay? So assume that a stop takes very little time, so it's just kind of like they stop, 25 minutes later, blah, blah, blah. Draw a line segment to model the situation. This is right here. The length of the entire segment represents the amount of time between trains, 25 minutes. A commuter will have to wait at least 10 minutes for the train if the commuter arrives anytime between 0 to 15. Okay, so between here and here, there's going to be an additional at least 10 minutes to go before you get to 25. Okay, so for this whole section, you're waiting at least 10 minutes. So the length of the favorable segment, favorable doesn't mean, favorable seems like in this situation, wouldn't favorable be you arrive right before the train arrives? No, favorable means it fits the particular conditions of what you're talking about. In this particular case, waiting at least 10 minutes, okay? So part of the timeline where you wait at least 10 minutes, that's the thing you're trying to find. That's what's considered the favorable thing. Matches this probability of waiting at least 10 minutes. Okay? So don't consider favorable to mean the thing that you like more. It means the thing that fits the situation you're looking to find the probability of. Okay? And in this case, there's a 15-minute window of time where you could be waiting at least 10 minutes out of the total of 25 minutes, the length of the entire segment. So when you simplify that by dividing by 5, you get 3/5. So there's a 3/5 chance or 60% chance or 0.6 chance that the commuter will wait at least 10 minutes for the train. Yep, that's it. Okay, here's your got it problem. And I've done you the favor of recopying this timeline here. It says, what's the probability that a commuter will have to wait no more than 5 minutes for the train? So, pause the video now, and when you have your answer, unpause it and come back and see how you did. Okay, we're back. So, what is the probability that a commuter will have to wait no more than 5 minutes? Well, what section of this would be waiting no longer than 5 minutes? Well, if you arrived here within 5 minutes of the train, then you would wait no more than 5 minutes. Okay, how many minutes is that? That is, so, and you could write this as, and you should write this as, probability of wait no more than 5 minutes equals, and how many minutes would you, is in this stretch where you would wait no longer than 5 minutes? Well, there's 5 minutes of time there out of the total of 25, and that simplifies to 1 out of 5. So there's a 1 out of 5 chance, or 0.2, or 20% chance of waiting no longer than 5 minutes. Yep. These you kind of, like, you can't, there's nothing you can do to just kind of follow an algorithm for it. You need to think about it, and you need to say, okay, waiting no more than 5 minutes means what in terms of the whole 25 minutes. Okay, so you really got to put some thought into it, but you can do it. Let's keep going. So when the points of a region represent equally likely outcomes, you can find probabilities by comparing areas. You can say point S, somewhere in region R, like we're going to randomly pick a point somewhere inside this quadrilateral. It's chosen at random. The probability that S is in region N, this triangular part of this larger area, is the ratio of the area of region N divided by the area of region R. Okay? That's the basic idea for that. So instead of it being a portion of a segment, it's a portion of an area. That's all there is. So let's apply that for the next two problems, and then we're done. Okay, so we've got a circle inscribed in a square, and point Q in the square is chosen at random. We're going to pick something that we know is going to be in the square. What's the probability that it lies in the shaded region? So it'll be inside the square, but it'll be outside of the circle. Okay, so the big idea here is we need to find the two areas, and we need to say, well, essentially, if you know the area of the whole square minus the area that's not going to be the favorable outcome, we will find what's left, the favorable outcome part. Okay, so what does that look like? Well, what do we know? We know the length of the side of the square, which is also the diameter of the circle. Okay, so what do we need? We need the areas of the square and of the shaded region. So what's the plan? The plan is to subtract the area of the circle from the area of the square to find the area of the shaded region. Then we can use it to find the probability. But remember, you find area with the radius, not the diameter. And what we have now for 6 is the diameter. So we need to then say, well, then what's the radius? So the area of the shaded region is the area of the square minus the area of the circle. The area of a square is just the side length squared, or 6 squared. And the area of a circle is pi times the radius squared. If the diameter is 6, the radius is half of that, 3. So you have 6 squared minus pi times 3 squared, or 36 minus 9 pi. And 9 pi is 9 times the irrational number pi. So you got to calculate that out on your calculator and then see what you get. And when you do that, you say, okay, so then what we do is we say the probability that lies in Q is the area of the shaded region out of the area of the square, because the square is the whole region. So the area of the square, we already know, is 36. So we say that 36 minus 9 pi over the total 36 for the area of the entire region of the square, right? And this is that region minus that. So that much, the shaded region out of the entire squares region, works out to be on the calculator 0.215 approximately, because you're never going to write it perfectly when you type in pi. Pi is an irrational number and you can't write it perfectly. So the probability that Q lies in the shaded region is about 0.215 or 21.5%. Since this is an irrational number, it's hard to write it as a ratio, but you can write it as a ratio like that exactly as long as you keep it in terms of pi. You should really read through this and make sure that you understand exactly what went on there, because I don't think it's like crazy hard, but you don't want to glaze over things and kind of sort of think you have them and not really deeply think about them until you get your mind around it. Okay, so review that, pause it and review it before we move on. But now we're going to go to the next slide for the got it problem. And here's what the got it problem says. A triangle is inscribed in a square. Point T in the square is selected at random. We're going to land somewhere randomly inside the square. What's the probability that T lies in the shaded region? Okay, so this is an interesting one because, well, you'll see what's going on there. But pause the video, calculate it, and then come back and check your answer against mine. Let's pause it now. Okay, we're back. So we know that this triangle, well, so first of all, we can say, okay, the area of the shaded region is equal to, and I can type it out. Maybe that's best. Area of shaded region equals area of square minus area of the triangle. Because everything that's not the triangle inside the square is going to be the shaded region, right? Okay, so once we have that, we say, okay, well, what is the area of a square? The area of the square, and I'm going to just write this out by hand, then the area of the square is the side length squared, and minus the area of the triangle. And what's the area of a triangle? 1/2 the base, and the base is just the side length, right? 1/2 5 times the height of the triangle, which the height of the triangle is exactly the same as the side length height, You might start to see what's going on here. And what you get is 25 minus half of 25, or 12.5. And so you get 12.5 is the area of the shaded region in square units. So, or I should say inches squared. So area of the shaded region, or the probability of landing in the shaded region, so we can say the probability of, what did they give us? T, point T in shaded region equals, remember what we do, we say the area of the shaded region, which is 12.5 over the area of the entire thing, 25, and fun fact, 12.5 out of 25 is exactly half, so it is either, you could write 0.5 or 50%, or of course that simplifies down to 1 over 2. That's the answer. Okay, one more problem and we're done. All right, so this problem is area of a circle, and what you need to do here is calculate and subtract things to find particular regions. But very specifically, let's read it. Okay, archery. An archery target has 5 colored scoring zones. Here's the white, the black, the blue, the red, and then that yellow center. Okay, formed by concentric circles. The target's diameter is 122, and if you can see that each band of 2 is 12.2. 12.2 times 10 is 122. Here's the 10. 1, 2, 3, 4, 5 to get you to the center. 6 to the other side of yellow. 7, 8, 9, 10. Okay? So the width of each of the zones is 12.2. The radius of the yellow zone, the radius halfway, is 12.2, right? So if an arrow hits the target at random, what is the probability that it hits the red zone? Okay, so what we need to do here to find the area of the red zone first, we're going to do the area of the red zone over the area of the whole thing will be the probability. But to find that area, we need to find the area of this circle minus this yellow circle. Okay, so to do that, first let's write it down. Well, let's take a look at how they wrote it down. Okay, the red zone is the region between a circle with a radius of 12.2 plus 12.2, or 24.4. That's from the center to the edge of the red zone. And the yellow circle that has a radius of 12.2. So you say, okay, the target then is a circle with a radius of, since it says it's 122 all the way across, it is a radius of half of that, or 61. So we're going to say that the area of the red zone, just the red part, okay, divided by the area of the entire target, means the amount that would land you in there versus the total amount, that will be the probability that the arrow hits that. So whatever the area of the red zone is, over the area of the entire target. Now to calculate the area of the red zone, we'd say, okay, it is pi times the radius squared. And what we need to do for the area of the red zone is, we say, the area of the red zone is the pi times the radius squared from the center to the edge, or 24.4 squared, minus pi times the radius of the yellow circle squared, right here, okay, over pi times the radius of the entire thing squared. And you can type all this in, calculate it all out, and you get it exactly equal to 0.12. Neat. Okay, and you can do that on your calculator and check it. So, oops. So the probability of an arrow hitting the point in the red zone is 0.12, or 12%. Worth actually looking closely and seeing what we did here, but essentially from the center to the edge of the red zone is 24.4. So that had this from here to the edge of the red zone has a radius of 24.4. So pi r squared minus whatever the yellow zone is, because that's not, that whole circle here encompasses the red zone and the yellow zone. So you got to take away the yellow zone. That's got a radius of 12.2, so pi r squared. That'll give you the just the red portions area over the entire target's area has a radius of 61. Okay, that's the idea here. So here it says, what is the probability that an arrow hits the yellow zone? Okay, so we already know that the area of the entire thing is this, and we already know the area of the yellow zone is this, so throw those together and figure it out. And also it says if an arrow hits a target at a random point, is it more likely to hit the black zone or the red zone? Explain. So you might want to do a little math there. So pause the video, and actually what I'm going to do is I'm going to see if I can cover this part up and not to hide it from you, but just you can write the numbers down that you need, but just to give you more space, more space to write. So I'll do that afterwards, and I'll do the work there. You can look at this now, unpause it when you have your answer, and then I will juggle things around and show you the work. Pause it now. Okay, so what is the probability that an arrow hits the red zone? So I'm going to grab some screen capture of this. The total area, I'm sorry, the area of the yellow zone. The area of the yellow zone is right here, this pi times 12.2 squared. Okay, so I'm going to take that down here, and out of the total area of the target, which we already know to be this right here, so we say that over that is going to be the probability that the arrow hits the yellow zone, and I can write that in words. P of arrow hits yellow zone equals this right here. Now, if we calculate this out, and I'm going to pause it and calculate it because I need to go get my calculator, and we'll find the number. And I'm going to leave this in terms of pi here. I'm going to say equals, and what we get is 148.84 pi over 61 times 61 is 3721 pi. And what you'll notice here is that they both have pi, and then pi can cancel out. And that's why you had an exact number for this last one, because they both had pi and it canceled out. So you didn't get it as an irrational answer. And when you do this calculation, you get 0.04 or 4%. There's a 4% chance of it landing in the yellow zone, which is the got it problem, part A. Okay, moving this up. So if an arrow hits a target at random, is it more likely to hit the black zone or the red zone? Well, whichever one has the bigger area is going to have the bigger, larger chance, more likely. Okay, so what do we get there? So I'm going to pause it and write some stuff down, and then I'll come right back and I'll show you. Okay, thanks for your patience while I did that. And here we have the original. They told us that the area of the red zone is pi times the radius of the entire center to red squared minus pi times the radius of the portion that's not the red section, or of 12.2 squared. And that calculates out to 446.52 times pi. I'm going to leave it in terms of pi. Now the area of the black region is the entire center to edge, which, by the way, if each is 12.2, it's 12.2, 24.4, 36.6, 48.8 is the radius from there to there. So pi times that radius squared gives you the entire black and everything inside of it, minus what we have to do here is everything that's not the black, and what's the radius of that? So 12.2, 24.4, 36.6. So we put pi times the radius of that squared, and we subtract it, and what we get is, in terms of pi, 1041.88 pi. Well, the question is it more likely to hit the black zone or the red zone? Well, which one has the bigger area? And of course, the black zone has the bigger area, and so therefore it's more likely to hit the black zone. That's the answer. That's the end of this lesson, and that is the end of all of the new material that you're learning for geometry. So congratulations. You still have work to do because you have to really master this lesson, and you have to do all the remaining work for the course, take the unit test, take the retest, and everything. But that's it. So if you can understand that, congratulations, and you can go get started on your practice IXLs, because there's a couple IXLs for this one. Good luck.